So welcome to the 19th Professional and Academic Development Series, PATS. As you know, PATS is an academic event organized by the emphasis in ELT education of the Interinstitutional Doctoral Program at Universidad del Valle and our research group EILA, Equipo de Investigación en Lingüística Aplicada. I also wanted to thank Professor Mayora for accepting to give this talk today. And now I'll pass it on to our host today, which is Professor Claudia Ortiz.
Thank you, Professor Alemar. So today, first of all, welcome everyone. We have the talk about, here I have it, correlation and sample linear regression in applied linguistics by Professor Carlos Mayora. So he holds a Bachelor of Education in English Language Teaching from Universidad Pedagógica Experimental Libertador and a Master of Arts in Applied Linguistics from Universidad Simón Bolívar. He is the head of the School of Language Science at Universidad del Valle, where he teaches language teaching methodology, the principles of language acquisition, and applied linguistics. His lines of research include individual differences in language learning, curriculum development, and language teaching methodology. So, Professor Carlos, can start.
Thank you very much to the research group and to the director of the PH program for this invitation. Well, thanks for the opportunity of sharing a little bit about this topic. So today, as you know, we're going to be talking about two, I consider basic statistical procedures. We're going to be talking about their theoretical or conceptual basis, how to interpret these or studies that contain these statistical procedures, and some of their application. Okay, well, so as it said, we're going to be talking about the conceptual basis, the interpretation and the application of correlations and simple regression. This is based mostly on a chapter by Norusian and Plonsky from 2018, but I have taken other chapters related to the topic as well. So I'm going to show you some pictures, and I would like you to tell me what two variables are involved in those pictures and what relationship can be inferred from those pictures, okay, or about those variables. Is that clear? Okay, this is the first set of pictures and the second. So I'm going to show it again. So what two variables can you see there, and what is the relationship between those variables?
Relatives.
Okay. All
Family
right.
members.
Marta says
Age.
age. Yes, because we have the years, right? Great, Marta. If we look at this, notice one of the relationships that you can see is weight and years, right? So the older the picture, the thinner I look. The more recent the picture, the fatter I am, right? So two variables, and low scores co-occur in both, and high scores co-occur in both, right? So that's the essence of a correlation, a relationship that happens in the measures between two variables, okay? Now, but another way to look at the same two variables would be this, right? If we're talking about hair and years, right? The lower the years, the more hair I used to have, right? And the more recent, the fewer hair I have. So again, there's a relationship, but this time the relationship is in reverse. High scores in one variable co-occur with low scores in the other variable, okay? In this case, as we're going to see, the correlation would be negative in orientation, okay? But that's basically the types of correlations that we might find. Again, two variables in which either high value or scores happen in both variables, or low scores happen with high scores, right? So a correlation is a type of analysis of association that identifies a relationship between two continuous measured variables. It identifies co-occurrence of high scores in one measure and high scores in a second measure. Now, the correlation, or the result of the correlation, is an index or a coefficient that is identified with an R, okay, which is called the Pearson product moment correlation index, or the Pearson correlation coefficient, okay? The R as an index ranges from -1 to +1, okay? So it can have both a negative or positive values. And it's always going to show association, but never shows causality, okay? The type of relationship that a correlation shows will never indicate a cause-effect relationship. Now, for example, when we have, let's suppose we have the two variables, and we put the scores in a diagram like this, or a graph like this, okay? And we see that all the scores, you know, low scores co-occur in both variables. Middle scores co-occur in both variables, and high scores co-occur in both variables. So when we draw a line touching all the scores, it produces a perfect straight line that touches all the scores. This would be an example of a perfect positive correlation, okay? A case in which in all the cases, there is this coincidence. However, perfect correlations are very uncommon and infrequent, well, in every science, but especially in applied linguistics. What usually happens is that you draw a line, and most of the cases, or most of the scores, group near the line, but do not necessarily touch the line. Okay, so this would be an example of a positive 0.9 correlation, which is a strong positive correlation. Now, we may have negative correlations, as I said, and in negative correlations, high scores in the in one variable will co-occur with low scores in the second variable. Okay, now in this case, the line that touches the cases, or that touches the scores, will go in the opposite direction. It will go downwards instead of upwards. Okay, but then again, in most cases, we will rarely or seldom find perfect correlations. Most of the times, we will find either strong or moderate correlations. So, some common or typical examples of correlations in applied linguistics. For example, listening comprehension and reading comprehension. High scores in listening usually co-occur with high scores in reading. Age of onset, or age when the acquisition process begins, and foreignness or accentedness. The younger the age, the less accented the speech. Attendance to class and grade point average. Those with higher attendance usually have higher grades. And learning strategies and scores in achievement tests. Those who report using strategies more frequently usually achieve better scores. Now, when we're talking about correlations, we need to consider the intensity, the orientation or direction, and the significance. When we talk about intensity, usually we consider that a 0.8 correlation is strong, okay? Moderate correlations usually range between 0.4 to 0.7, or weak correlations are 0.3 or lower. When we talk about the orientation, we're referring to whether the correlation coefficient is positive or negative, right? Remember, positive then would be that it goes upwards, and low scores go forward with low scores and high scores with high scores. And negative, the line goes downwards, and high scores go forward with low scores, right? And finally, the significance, or the p-value, that is, according to probabilities, how reliable or how valid or how significant, statistically speaking, the results are. So correlations are considered a non-directional measure. We have two variables, but we want to establish, or what we want to check is the relationship between, or the similarities, or the level of overlapping between the two variables, okay? But notice that there is no effect of one variable over the others. If we consider this example, which was a very silly example, but if we consider this, we have the weight and the years. Can we say that the weight causes the increase in the years? Obviously not. I mean, the years will move, will advance, regardless of whether or not the person weight increases. The other way around, is there something natural in the passing of years that makes the weight increase? Neither, right? So this relationship, what might show is another latent or underlying variable that produces the relationship, or that is affecting both variables, okay? Or at least one of them. But there is no, one is not affected or affected by the other. Okay, so far so good, right? Yes, I guess. So something that is important to consider is that the higher the correlation coefficient, right, the more the grouped or the closer the scores will be in the regression line, okay? So, for example, here we have a 0.9 positive correlation, and you can see that the scores tend to group together, right? Like they gravitate around the regression line. If we had a correlation of 0.5 or 4, the points or the scores would be more dispersed. So let's check how clear it is with this game. It's a game called Guess the Correlation. So in this game, they're going to give us a scatter plot, right, without the regression line. And we have to try to guess what the value of the correlation coefficient, okay? And when we have it right or very close, our guess is right, or at least very close to the actual value, we will get a point. When we get too far, or it's not close at all, we will have a life. We'll lose a life. Okay, so if you see these scores, what do you think is the coefficient, the correlation coefficient? Take a guess.
Positive.
Positive 0.7.
It's positive, great.
0.7. 7.
0.7.
Yes.
Okay. So 0.7. No, the true value would be 0.84. The difference was higher than 0.1, so we lost a life. Okay, what about this one?
That's 0.
Negative.
0. No correlation.
No correlation at all?
1.
Very, very weak. Yeah.
Okay, should be very weak.
Wine. Yeah, 1 or 2.
Yes, we got it right. Okay, the true value was 0.11, and we are in a difference of 0.0, so it's correct. Okay, so we recover the life we lost. Okay, what about this one? How these pairs or grouped are the scores?
1.
Again?
Could be like 3
Higher, yeah.
or
Like
yeah, 4.
15.
5 or 6.
Okay, enter.
Or 6? You tell me.
5 or 6.
Like, yeah, 5 or 6.
Wow.
Is like,
Okay, so let's say 55. To put it in the,
Okay.
in the
let's
middle.
say.
Okay.
Yeah.
Wow.
The
It's
true
higher.
was, yeah, so we got, okay, it was 0.62, but we are in the 0.10
Difference. Yeah.
percentage of error, so we got an extra line.
Okay.
Good. Okay, what about this one?
It's very
Alright.
strong. Yeah, very strong positive correlation. Should be 9 or 8. Yeah, 9.
9.
9 something.
Yes,
Yeah.
correct. The true value was 96, and we are in the,
Oh, Marta said 95. Wow.
Very close.
Oh.
Almost nearly there.
okay, what about this one?
Yeah.
It's all
That's-
scattered. Could be
1, 5.
3.
Maybe.
0.15, 0. something?
That's too low.
Too low.
15. Yeah. Or
That's too low. Maybe higher.
21.
Maybe 3. 0.3 maybe.
Okay.
20.
3 or 4.
Okay.
So a little bit
0.4.
higher, but
Okay.
still very low correlation. Yeah, very weak.
Yeah, still a very low correlation. Yes, this number in a way tells you that that co-occurrence happens 40% of the cases. Okay, when you have 0.8, it means that in 80% of the cases, the co-occurrence of high and low scores happens, right? But it's when it's just 0.40, it's only 40% of the cases, these co-occurrence of scores is actually happening. That's why we have to be careful when we have low correlations or weak correlations, because we might be making generalizations that are completely correct. Well, let's try one more. This one.
93.
Okay.
95 maybe.
Okay, but we all
95.
agree that it is above 0.9.
Above 9. Yes.
Yes, actually,
96.
96. Okay, so actually, sometimes only with the scatter plot, you can see whether there is correlation or not, without even calculating the correlation coefficients. Okay, well, you're great. Okay, so let's go back to the presentation. Okay, so whenever I want to find relationships, similarities between variables, then I use correlation, but I cannot state any cause-effect relationships, okay? Now, something more. The R, the correlation coefficient, shows to a certain point how much two variables overlap or how much they are similar. When we square the correlation coefficient, what we get is an index of the shared variance. Okay, that is the variance that both variables have in common. So a correlation shows the degree of overlap between two variables, or how much two variables vary together, okay, when they have high scores and when they have low scores. So the square value of the correlation coefficient shows the percentage of variance both variables share. So if we represent the variance of the two variables, right? What we find is that when there is no correlation, there is no share variance. But when they have a correlation of, for example, of 0.6 and you square 0.6, that means that they share 36% of the variance. And if you have a correlation of 0.8, that means that they share 64% of the variance. Now, the variance is of how much difference, how much dispersion there is between the cases of one variable. And this means that if two variables share a high percentage of the variance, that means that they are both affected or they are both influenced by some other external variable. This concept of share variance is also going to be important to understand the next procedure, which is linear regression. So let's take a look at simple linear regression. Okay, this is going to give us another important procedure, and we are going to understand the key difference between correlations and regression. Okay, simple regression is a type of association analysis which makes explicit the directionality of the relationship between variables. Beyond mere association, it can establish a causal relationship and prediction. Okay, so usually we represent it like this. X is going to predict or affect Y. So one variable is going to have an impact, or is going to predict, or is going to explain the other one. Okay. So when we talk about correlations, we cannot talk about dependent or independent variables, or we cannot talk about one variable affecting the other. But in simple regression, we do. In fact, we have to talk about this kind of cause-effect relationship. Now, the mathematics of the simple linear regression and of Pearson's are the same, except that simple linear regression is directional and sensitive to the role of variables, dependent versus independent, in the research question being posed. Okay, so when I formulate the research question, I have to have clear which variable is going to affect or impact the other. While in correlations, I don't need to establish this kind of relationship. Okay. Okay. So now let's take an example. This example is from Lowy and Satan. The Plonsky and well, the chapter that I read, it had an example, but it was mathematically more complicated. This example from Lowy and Satan, it's I think it's going to be much more or much easier to understand and to follow. Okay, so they said a question: how much motivation plays a role in learning a language? Okay, so we have two variables: motivation and learning a language. And we want to show that this one has an effect over this one. So the first thing that we need is to establish how we are going to measure them. So motivation, we can measure it or establish it, for example, or Lowy and Satan in their examples define it in terms of hours spent studying the language. Okay. and language learning as the results in a proficiency test. Okay, so I have to have two continuously measured variables. Variables that are measured in terms of numbers and in terms of the scales, rather than nominal or dichotomic variables. Okay, so when you have the data, you establish the number of participants, how many minutes they spend studying, and their test scores. And you run mathematically a procedure that is very similar to that of the correlation. Okay, so you have your time studied, you're going to have the score, and using, well, you can do it in Excel, but of course, it's better to do it with a special package for statistical analysis. Okay, and you establish that you want a regression, that you want it to be linear, etc. And it's going to give you a result that is called a model. So in the model, you're going to have a coefficient that this time is called the capital R. Okay, the capital R. Oh well, we're going to see each of them in a minute. After the capital R, you have the R squared. Okay, which is basically, you know, when you square this value, I mean, you multiply the value by itself and you get this score. And then you have the adjusted R squared. And then you're going to find the standard error of the estimate. Okay. So the R gives us information about how much our straight line fits our study data in the scatter plot, the regression line. It is the same as the correlation coefficient, or the same as the Pearson product moment correlation, but with no negative values. It ranges from 0 to 1. So this is going to be the same value as a correlation coefficient, but it's always positive. Okay, it's always going to show an upward regression line. Okay. Now, the R squared provides the area view of the amount of variance in the dependent variable that is predicted or explained by the dependent variable. Okay. So remember when we were saying this, that R squared shows the share variance between the two variables. So the capital R squared not only tells us how much variance both variables share, but it actually tells us how much the independent variable explain the variance in the dependent variable. Okay, that is, from the different scores that students get in the proficiency test, a 17% of that dispersion is caused by the time they spend studying for that test. Okay, is that clear? So this variable alone explains 17% of how different the scores in proficiency are. Okay. Now, and the adjusted R squared is the value, well, it's adjusted for best fit considering a number of design features. Usually those design features include the number of cases, the number of participants, the reliability of the instruments, okay? So the closer the adjusted R squared is to the original R squared, the better, okay? If you got a very large difference, so it means that many of the design features of the study were inappropriate. Okay, so when you have the adjusted R square, then you can say that your independent variable, time studying for a test, explain, or you can even say that produces 13% of the changes in the dependent variable in the scores in a proficiency test. Now, the SPSS is going to give you a second table of results. It's going to show you the progression, the residuals, etc., the sum of the squares, the degrees of difference, the mean square, etc. But all this is to estimate an ANOVA, an analysis of variance. And this ANOVA test produces an F value, and with the F value, you can calculate the P value, how statistically significant that relationship should be. So we're not going to explain all of these numbers, but basically in this second table, what you have to look out for, what you have to be careful about, is whether the ANOVA model is statistically significant, and it's usually considered significant when the p-value is lower to 0.05. Okay, that means that there is a 95% confidence of the probability of the results. Here is explanation. The regression SOS is the sum of the squares of the scores of the dependent variable that are explained by the dependent variable. The residual is the sum of the square of the score that are not explained. Okay, but then again, what you should care for is the significance. Okay, if it is not significant, then the model is not fit for the data. Okay, and the last table that a simple regression would produce is this. Again, it has what is called the constant, okay? It has the B coefficient, and it has the beta, okay? And then it has to calculate the significance of a t-test. Now, what this means is the following. The constant, or the intercept, is the score in the dependent variable a student would get if the value of the independent variable is 0. So that's the score a student would get in the proficiency test if he studies 0 minutes. Okay? If I have an independent variable of 0 minutes studying, I will probably get the constant. I would get 17 points in that test. Now, the independent variable in measure is called the slope, or also the B coefficient. This is the amount of increase in the dependent variable for each unit of increase in the dependent variable. And this is actually a prediction. So, if we see the value of B is 0.062, that is, for each additional minute studying, the student would get 0.062 more a higher score in his or her proficiency score. And finally, the beta is the amount of increase in the quantity of the dependent variable for each standard deviation increase in the dependent variable. And this represents a more accurate prediction. Of course, well, it's more accurate, but mathematically it's more technical. So, and difficult to get, but that is, for each increase in one standard deviation in the dependent variable, a student would get 0.416 more points in the proficiency test. So we can look at it like this. We have number of minutes studied, we have the score in the test. So here, this point here is the intercept, which you should remember is 17. Okay, so the score I would get with 0 minutes study. Then the B coefficient, also called the slope, tells me how lean or how inclined is the regression line. So it's usually represented as an angle. Okay, this is the regression line, the R value. And finally, the beta, which is not represented here, is going to tell me how much would increase for increases in the standard deviations. And the standard error will tell me this. Let's say normalize, right? Average of the different distances from each core to the slope. Okay, so it makes an estimate and tells me a number that represents if the actual scores are too close or too far from the regression line. Okay, so, and of course, as in any case, we want the standard error to be as low as possible. Okay, if we have very high standard error scores, well, it means that our data or our model will be the least reliable. And it would mean that the points here would be more dispersed compared to the R, okay? And it will also show a very low value of the R or the correlation coefficient. So this is how the simpler regression works. So in this example, in this case, the intercept is 17. So when a student does not study for a test at all, the outcome is likely to be 17. The value for the slope in this case is 0.062. This means that for every minute a student spends on studying for the test, the score will increase by 0.062 points. If a student studies for 100 minutes, the score will be 6.2 points higher than 17. Okay, this is the way that you interpret this kind of prediction. I mean, in simpler language. Okay, so once you understand how much percentage of the variance is explained by your variable, then the idea is that you try to manipulate that variable so you can impact or affect the dependent variable. Okay, so in this very simple example, the conclusion is that you have to foster your students to spend more time studying before a test. Now, another thing is that, of course, here you explain roughly a 13% of the variance in the dependent variable. So you have to find for the variables that explain the rest. I mean, there are many other variables that are explaining over 80% of the variance in the dependent variable. So when you want to add more variables to create the model, that is multiple linear regression. Well, in this case, we're talking about just a simple linear regression, but you can add as many independent variables as you want. And of course, the more variable that you add, the more percentage of the variance that you can explain. So some assumptions that you need to take into consideration when you're going to go for correlations and simple linear regression. For example, for correlations, each variable should be continuous. With regression, you can use ordinal variables that represent categories, but in which the order in which they are presented is important, okay? In which a number 5 actually means something different than a number 3, okay? And that you cannot alter that order. For both, it's important to have low error or standard error and high reliability, especially if you're using instruments. For correlations, it's recommended that you have at least 30 participants or at least 60 scores, 30 in one variable and 30 in the other variable. Absence of outliers. Outliers are those scores that are way too far from the mean, that are, to the extreme, either above or below the mean. So when you have those very high scores, most statisticians recommend to take them out of the study. Okay, imagine that you want to, I don't know, correlate income in Colombia with some other variable. I don't know, with the level of happiness. If you include, for example, senators and the president, whose salary is, above 20, 25 million, those are outliers. They are going to produce an inflated mean. Okay, so to have reliable correlations, it's better to remove those outliers from your sample. Normality. Both type of statistic procedures require that the data fit into a normal distribution. The normal distribution is, as you know, represented by the gauge bell, right? It's this shape like, yeah, it looks like a bell, okay, in which the mean, the median, and the mode are the same, or at least very close together. Linear relationship is that you can find, that you can actually, well, especially this is not for correlation, it's for regressions. The variables that you include for the regression should correlate, at least partially, okay? Not necessarily perfect correlations, but they have certain degree, at least weak correlations. Otherwise, it's unlikely to find any relationship between the independent and dependent variable. And the other one is homozygosity in regressions. That means the degree of similarity in the variance of all the included variables. So both the independent and dependent variables should have similar or almost equal variance levels, which you can estimate using the standard deviation. And then, well, these are some sample research questions. For example, what is the relationship between study habits and academic achievement in an intermediate English course? Do you think that that question can be answered using a correlation or a regression?
The first one is a correlation.
Correlation, that's right. What is the effect of socioeconomic status on Colombian students' performance in a standardized test of English?
That's a regression.
Yes. What affected variables, motivation, self-esteem, attitudes, best predict willingness to communicate in French as a second language?
Regression.
How is performance in an L1 literacy task related to performance in an L2 literacy task?
Correlation.
Correlation, exactly. And what is the effect of previously known languages in the development of English as a third language?
A regression.
Regression, right. So whenever we're talking about the effect, the inference, prediction, we're talking about regressions. If we're just talking about similarity, relationship, some sort of connection, we would be using correlations. Okay. So what are some of the applications? For example, correlations are usually used to determine the reliability of assessment instruments or data collection instruments. That is, if a test or a questionnaire is to produce consistent results, so the results of a first, a second, and even a third administration should correlate, should be similar, right? Identify the latent construct. Again, correlations do not show you cause effect, but they can show you that probably the two variables that correlate are affected by another or a third variable that is not explicit in the measure, okay? And it can be used to at least try to infer what that latent construct is on the line. Concurrent validity of instruments, whether you want to determine that your test or your questionnaire is valid, you can use correlations of the results from that instrument with similar validated instruments. Another way is a procedure called factorial analysis. Factorial analysis is basically based on correlations. And finally, how to determine or to produce fit models with predictive power. So if you, apart from finding a relationship, you want to find some kind of cause-effect relationship, and you want to make predictions based on that, not only of the same population, but for similar populations, then you have to use a regression, especially, well, if it is multiple regression. And well, that was it. Thank you very much for your time, for your attention.
So, well, thank you very much, Carlos. Thank you, everyone, for attending. Thank you, Claudia, for hosting. So thank you very much, everyone. And thank you, Carlos, again.
Well, bye-bye, everyone. Thank you.
Bye.
Have a nice weekend.
Bye.
Bye-bye. Thank you.